Good morning, everyone, and welcome to the Simu Talk podcast. My name is Julie, and this is my co-host.
Hi, I'm Scotty.
So today we have a really exciting client here with us. We have a customer that we've been doing business with for over 11 years. It's a company called SCIEX. They're a life and science technology company, and we have a self-starting engineer who is a lead simulation engineer at SCIEX. His name is Amir Seif. Hi, Amir. How are you?
Good. How are you, Julie?
Good. So one of the ways I want to get this podcast kicked off, just to make you feel a little bit more comfortable, is I know you have a lot of technical background, but just tell us a little bit about something maybe personal about yourself to for us to get to know you better.
Sure. So what I could say is I'm like probably many of your viewers, I'm a dad and specifically feel very blessed that I'm a dad of actually a 7-year-old autistic boy and a 4-year-old daughter. And they pretty much, besides my technical endeavors, they are my life.
Amir, how would you describe what you do to a 5-year-old?
Actually, I get that question often from people who are not technical, whether that be a neighbor or someone new I've met. And it's usually, well, what does it mean to be an engineer? Some people have the misconception that we actually build stuff. And I mean, I've never touched a tool in my life. I wouldn't know what to do with a tool. And I respect the guys who actually fabricate the parts because that's not what an engineer does. And of course, you've got design engineers and then you've got analysts. Well, I'm on the analyst side. And what that basically means is I make sure theoretically through, doing all this computer programming stuff and looking for hot spots and dangerous spots, I make sure that airplanes don't fall out of the sky. I am like many of the other engineers that make sure buildings are not going to crumble, that they're strong enough and safe, or that safety railings are not going to break apart. You're going to fall. That's what engineers do. We help create plans and designs for cars and trains and houses and all the things you see around you. We make sure that they work and that they're not going to fail on you. And we do that before anything's ever actually made. So we try and use math and physics, and that's why you go to school. So if your kids ask me, what am I going to ever use this math for? This is what you use it for. You use it to make your iPads and your laptops and your cars and your trains and your buses and all the different things you interact with the world. There was an engineer involved in that, and they make sure it's either safe or reliable and just quite honestly, cool looking. That's the kind of stuff that we do.
Has to be cool. Yes.
Has to be cool.
Engineers
Absolutely.
make the world, honestly, a better place. We wouldn't have all these cool things without you guys. We wouldn't even have this, but we probably wouldn't even have this little microphone here. So
it pretty much is our job to think as the laziest individuals on the planet and figure out how to make jobs even easier than they already are.
I know that you started in the aerospace industry as a mechanical engineer. Tell us about how you got started using Ansys or even in the aerospace industry.
Sure. So I actually did both my bachelor's and my master's at Ryerson University. And my first interaction with Ansys was very, very basic. It was in classical Ansys and APDL, and it was first year, second year bachelor's, and it was make a little truss. And very, very simplistic. And then I never touched it again until my master's. And in my master's, again, I was kind of just thrown into the deep end. And it was kind of like, figure this out or you get an incomplete on your assignment. And I figured it out, played with it a little bit more. But where things really picked up for me is after I graduated with my aerospace degree, I got a job at Pratt & Whitney Canada. My supervisor at the time, he was also my student supervisor, Chao Zhang, actually taught me everything I knew in Ansys mechanical APDL. And primarily in my role there, all I did was mechanical simulations. So I didn't get exposed to all the different physics that I've been exposed up to this point. But that was really my beginning of where I started on my path to becoming a self-proclaimed expert in Ansys.
Yes, you definitely are. I mean, now experienced with, mechanical fluids and electronics, it's very exciting to hear some of the stories you have to share for sure.
Of recently, the other physics I've really been exposed primarily just at SCIEX, where they seem to be pushing the limit on everything. So I've just been continually asked, well, can you do this? And my immediate response is, of course I can, even if I don't know how to do it yet. Then I go and figure out how to do it. I've always been like that. So even at Pratt, if I was told that, something couldn't be done or something's not set up right, for me, that's just you're just telling me that you need me to do it. So I'm going to go figure out how to do it. So I was one of the first at Pratt to start using parametric optimization through Design Explorer, and literally took a process that was taking 6 months and dropped it to a couple of weeks by utilizing that tool. And the real funny thing about that whole story was that Pratt was actually paying for that license for multiple years, and no one had ever used it. Almost no one was even aware that it was there.
Until you came along.
Until I came along and actually noticed that there's this funky little license that shows up on the license server, but it never gets usage. And I didn't really know what it was until I started diving into a specific assignment that was given to me. And I just felt that the way it was being done was too slow, and there must have been a better way. So of course, when I started digging into the tools I had available, which was Ansys, I found that there was this Design Explorer feature. And then of course, I went digging and asking questions and figuring out that most people didn't even know what it was for and didn't even know they had it.
So you kind of just put your little Ansys cape on and swooped in like a little simulation superhero.
Pretty much.
I love that. You know, one of the things that we kind of wanted to talk to you about career-wise is that you are obviously a self-starter. So you've taught yourself all of these things. You say yes to things that you don't even know how to do. So how did you kind of get there? I mean, how did you teach yourself how to do all of these amazing things? Like, how did you become so talented as an engineer?
It's a mixture of both. Part of me always wanting to challenge myself, but also a big part of it was being lucky to be exposed to some really brilliant people. Just like, for instance, Chao Zhang at Pratt Whitney. I really say that in the 10 years or so of school that I went through to become an engineer, I probably learned more from him in 11 months than I did in all my time at school. And it's just because he was that fundamental to the things that I needed to learn, and really pushing me where it was kind of like, this is what I need done. I could do it myself, and I don't have the time to teach you how to do it. So here's the manual, and here's some blogs, go figure it out. And then my part, I just took the challenge and taught myself, did the reading that was required, and stumbled and falled. And I mean, at times, especially when you're working in mechanical APDL, it can seem very overwhelming. And it is. And when you start working with it, because there's a great deal of power that you can leverage, you are going to fall, you are going to fail. But every time you fail, just, that old saying, get back up on the horse and keep trying, it'll work eventually. Well, it did for me. Every challenge was just hours of frustration until I got it. And then that one moment of complete jubilation because I figured out the problem and I could finally do something that most people couldn't. And it was just sheer effort and continual challenge to myself to just try new things and not being afraid of failing.
We do have a lot of viewers and listeners who are just getting into Ansys, and the common theme that we see from a lot of people is that it can be very overwhelming. In addition to some of the things you've already said, is there any kind of advice that you would give to like a novice or junior engineer getting into it?
A part of it is circumstance, but if you can find that person that could be a mentor that can teach you some things, even if it's not a direct class or a direct teacher or anything like that, but just someone who seems to know a lot and that can give you some pointers on doing certain things in different physical environments. That I think was most fundamental. And like I said, it doesn't have to be a whole bunch of people. For me, it was really one man. And that was Chao Zhang for me, especially when it came to APDL. The rest of it is just don't give up. Keep pushing. It is complex, but with the advent of Workbench in the interface, it's made a lot of that easy. And so my advice to a junior engineer or even a senior engineer who's just diving into Ansys for the first time, don't be satisfied with just knowing how to click the buttons in Workbench. It is of benefit to you to actually learn the APDL and the background programming. I mean, I went as far for one of my master's projects to pick up a new language. I learned a little bit of Fortran so that I could customize Ansys to do something unique. If I didn't go through those challenges and I didn't go through all those hours of frustration to figure out how it works, I wouldn't have achieved those goals that I did that ended up getting me my master's. And along those lines, by producing good work and then trying to share it, I went through a lot of effort in my thesis paper to try and make sure that whatever I went through and the things that I accomplished, I wanted them to be repeatable by other engineers. And I've actually had 2 random strangers reach out to me over LinkedIn, simply saying that, your thesis was so well written that it was easy for us to actually mimic your work. And it was pretty much the easiest user guide we could find online because nobody else explained it as well as you did. And to me, that was rewarding to know that I had helped someone who probably was a novice user of Ansys. just by giving them something. So those blogging communities, they're very valuable. If you know what to ask, it's a lot of Google searching, but I mean, World Wide Web helps. So keep plugging away, keep trying, use those blogs because they are helpful. There are more and more communities that are being set up dealing in finite elements in general and simulation. But if you can, find that one good person to be your mentor and just stick to them and learn and absorb and everything you can get from them. And that's what happened to me. That was my starting, was Chao Zhang. I can't repeat that name anymore. Like, he really is fundamental to me. And
Yeah,
still a person that I keep in contact to this day because he meant that much to me in my engineering career.
that's
Well,
amazing.
kudos to you for that. It seems like you're also doing that for others as well, especially people reaching out to you on LinkedIn and extending their thanks to you for helping them out. So maybe, you're kind of being that for them as well. So that's amazing.
Trying
Um,
to, because that's the most important thing, is to try and share that knowledge.
yeah. So, I mean, it's clear to us that you see the value in Ansys. So maybe for the viewers listening, if you want to explain a little bit about how crucial it is to have Ansys for a product in technology development stages. I don't know if you want to elaborate a little bit on that with SciEX and how when you got started, how you've brought SciEX from when you got there to where it is today. Without Ansys, how would you guys have gotten there basically?
What I would say is that, as you mentioned, I only joined SciEX 3 years ago, but they've actually had Ansys for a lot longer. And I think at most places that I've been, whether they were using Ansys or another finite element software, the common theme that I've run into is that they have the tool, they just don't know how to use it. And in some cases, they think they know how to use it and they just don't trust it. So I've
Okay.
been in environments, for instance, where even at Pratt, I had a very large engine model that was passed down to me to take a look at. And I noticed that they had made some oversimplifications. And when I kind of corrected those that I saw as oversimplifications, we immediately captured hotspots, exactly where testing was showing cracking. Well, now I went from, let me see this model, refine it better using Ansys, to actually being able to use that data from Ansys to predict how long the crack would take to propagate and until it would become unsafe to fly with. So imagine having a part in an engine cracking, but we were able to be so accurate between testing and simulation to be able to decide when the part had to be removed for overhaul while it's cracking, because we could predict how long that crack would take to propagate. And now at SciEX, we're now going from a stage where early on it was kind of like, well, let's use Ansys because now we're in a put a fire out situation. We've already got a problem. And let's just see what Ansys can tell us that might help us out in all of our expensive experimentation. Now that mentality is shifted and the designers are starting to say, hey, before I commission a part, why don't we go and ask this guy if he can simulate it and basically point out our weaknesses for us?
You guys figured it out the hard way. We want our
Yes,
clients, yes, we want our clients to figure out their problems before that. So
absolutely.
that's amazing.
I actually working on a specific project that's pretty tight and they haven't ordered any parts yet. So this is really the first time they've really come to me early on. They
Okay.
know they kind of have a problem and they're trying to fix it on the next generation of instrument. And it's specific to do with an actual detector and its flatness from manufacturing. And then after they assemble it, it deforms even further, which actually affects the performance of the instrument. So now they want to create a fix, but they want to know where their problems actually lie before they try and create a fix for it. So I've literally got the entire design community in the detector group waiting on my results so that they can make an informed decision of what the solution is going to be.
Wow.
And that's literally what I've been working on for the past 3 or 4 weeks. So there's even talk of going multi-physics with that, is that, okay, do the mechanical simulation for the deformations, and then bring that data into an electrical simulation and look at the impact on the electric field, which is also fundamental to the operation of the instrument.
So what tools of Ansys would you be using for that?
So I'd be using Ansys mechanical APDL, and
Okay.
then I would be carrying that information into Ansys Maxwell.
You talk a little bit about training and self-taught and self-starter and you're kind of the simulation guru now. So how did you learn Maxwell? I mean, Maxwell is not an easy tool to use, so how did you learn how to use Maxwell being a mechanical engineer?
Well, I kind of was kind of given the challenge, and it was kind of like, we need this type of simulation. Can you do it? I just jumped right in, opened the program, and click some buttons, see what happens. But more than that, looking for YouTube tutorials on the most basic, simplest examples, just to get an idea, feeling of what the environment is like. Asking a lot of questions from my technical experts and a lot of the electrical designers, talking to them about the fundamentals that I may have forgotten from first year university when we did our first year circuits. Because it's not enough to just know how to do the simulation and understand the computer. You should at least have a basic understanding of the physics and the math that's involved in those calculations. And then, of course, a step further, which I found was extremely helpful, is I actually logged into that SimuTrain portal and used a lot of the tutorial and the documentation that was there to really get me up and going on more than just the basic tutorials that you could find on YouTube. It was really the SimuTrain that really gave me a good feel of what Maxwell was. And then, of course, I went a step further, and I'm grateful for the great relationship that I've got with the Toronto office simulation engineers there at SimuTech.
Anybody name you want to mention?
Zoe actually is the one that I work with a lot. I mean, every time I've got a problem, and Natalia, there's another, those two ladies.
Wow.
I'm surprised they haven't just stopped, answering the phone whenever I call, because they spend hours sometimes helping me review a model. No matter how complex it is, they'll review results and look at things with me and try and understand with me why my model may not be solving, or if there's a better way of doing it. So really that relationship at this point, especially at SciEX, this is the first time I've been in a position to really leverage that relationship. And it goes along those lines of finding a good mentor.
Yes.
So although I've never been in a relationship where I really wanted to do any of the one-on-one classes at SimuTech, but that mentoring from other experts at SimuTech has been fundamental to my success thus far at SciEX. Being able to leverage that relationship and speak to other engineers who are experts in that particular environment has been profoundly important for what we do at SciEX.
That's awesome that you have that relationship, because I mean, with my clients here as well, they find that, they can just, with SimuTech being such a smaller engineering organization, they kind of have their favorite engineers that they just pick up and call for help, Oh, hey, Zoe, I have a problem. I need your help. Are you free? And it's kind of like they're your friend, or,
Absolutely.
It's great to hear that you have those relationships. Julie and I will definitely go talk to Zoe and Natalia after and say, great job working with Amir.
I mean, even I believe it's Ian is usually my guy for CFD, and same thing there. Spends hours with me when I've got a difficult problem to solve, and is always ready and willing to Zoom, in these crazy times where everything's being done virtually. He has no problem coming on and sharing my screen so that we can look over a problem together. So that's been super helpful.
When you are working on these different projects, is it typically one model and you're analyzing one discipline at a time, or is it kind of you're taking that same model and you're carrying across all the different disciplines, running it through the different multi-physics?
Thus far, it's been primarily staying within that one environment, as basically the electrical department is only really interested in their electric fields, and then they don't really ask me to do anything else. Or the research scientists who are mostly interested in the fluid flow only want a CFD and are not interested in the mechanical implications. That is quickly changing. The detector group are typically only interested in electrical. But now there's talk of, can you take a mechanical and look at the deformed shape and then tell us multiphysics, what does the electric field look like because of that mechanical simulation?
Right.
That's happening more and more. I know it's going to get to a stage where there's talk of trying to customize fluids to create an ion trajectory calculator that accounts for both the electric field influence on the ions as well as the fluid velocity fields on the ions. So that's a multi-physics application that needs a lot of development, but it's definitely top of mind in the organization in general. So it's kind of like, it's not a matter of if we will, it's a matter of when will we. It's something we need to have, and it's something that's top of mind that eventually we have to develop that capability. So there'll be more and more of that interaction going between all three, going from fluids to mechanical to electrical, and it will be the same model brought across all the different physics.
What would you tell a new engineer who is maybe just starting to get comfortable with mechanical Would you encourage them to kind of try out and reach out to other departments to see where they can help out, or would you just say, do what you do best and kind of stick with that? I mean, it sounds like maybe it's just not for everyone, but at the same time, it sounds like if you're looking for opportunities, the opportunities just kind of arise.
I do believe that a lot of the skills that you would gain, say, if they are primarily just getting comfortable with mechanical, a lot of the skills that you learn there are transferable to the other physics. So the only thing I would say that would stop a junior engineer from going into the other physics is if you really, really have a dislike for a different type of physics, not because of the simulation, but let's just say you absolutely hated electrical circuits and all that, and you never wanted to touch it again when you left school. Well, you may not want to take up electrical simulations because you're going to have to deal with that stuff. That being said, I myself actually hated circuits, and that's why I brought it up.
Mm.
And I think it was more of when I took it in school. Unfortunately, I think my prof just didn't know how to teach it that well, and or I just didn't communicate well with him, and I didn't get the concepts at that time. It didn't stick with me. But now being and as you gain more experience as an engineer, forget just simulations, but as you gain experience and exposure to different problems, it was just like when I studied aerospace, I thought for sure that I would want to do aerodynamics for the rest of my life. When I finished school, I realized I hated aerodynamics. I wanted nothing to do with it. I wanted to be completely mechanical. I was interested in material sciences, in stress analysis and deflection analysis. But now I just see all those problems as beautiful problems, whether they're electrical, whether they're fluid, whether they're mechanical. All the physics appear less daunting now that I've gained more experience. So if you're a junior engineer just starting and it seems daunting, the more experience you're going to gain, the less daunting all of the physics will appear. And then everything will become interesting. It just becomes engineering. And there's
Right.
no longer a differentiation between, well, I'm a computer engineer or I'm a chemical engineer or industrial engineer. It doesn't matter. It's
Yeah.
just beautiful because it's engineering.
So I think one thing that is also interesting that you mentioned is it's important to find that mentor. Unfortunately, some of the customers that I've talked to, they are the only engineering simulation person there, right? And so what kind of suggestions would you have for someone if they are the only person within the whole company? How would you suggest them to go reach out and find that mentor that you're talking about?
It might be pretty difficult, but I'm in an odd position where I can offer some advice on that matter, just in that in cooperation with Robert Scriven at SimuTech.
Hmm.
He's actually our account manager basically for SCIEX for all of our products, everything we buy, right? But between himself and I, we have this personal initiative that we've started, and it's actually a Canadian user group
Oh,
for
okay.
simulation, and it covers everything. And we have what we've been attempting to do, and because of COVID, they've been virtual, but they're basically virtual user group meetings where you
Oh,
get to be exposed to actual engineering professionals who use simulation. And it doesn't necessarily have to be Ansys, though many of us are Ansys users, but it is a great place to be exposed and see what others are doing in other companies, but also a good opportunity to network and find your mentor where you can ask questions, because you could be in the middle of the group and just say, hey, listen, I'm solving this right now, and your problem's very similar to mine. How did you deal with this? And you'll have a whole panel of experts who can answer your question. So finding groups like that, and I'm mentioning it now, it's on LinkedIn, they can look it up if they'd like, is a great way, is just trying to find that network of other engineers that you can connect with. And you might find some just over other social media as well, other groups
Hmm.
involved in simulation.
For the listeners who are probably scrambling on LinkedIn trying to find that group, what is that group called, and are there any rules or regulations to join it?
I'm not the one who set up the LinkedIn account, so I'll have to check for the group, but I'm not sure if you have to be invited by one of the admins. So it'd be kind of like email one of us and we could get you in kind of thing. But I can check with Robert to see how that works.
awesome.
But other than that, I mean, there's no requirement that you have to be this. I mean, you don't even have to be an engineer. You can just be a simulation enthusiast and join. And the idea is that we do these quarterly presentations to just kind of let everybody know what we're doing. what's going on in the world and what new toys we're playing with.
So you mentioned using other simulation tools, and I know this. I know Ansys is your preferred tool. So tell us, what is it about Ansys? Is it the accuracy? Is it the solver capabilities? Tell us a little bit about why Ansys is your preferred tool, or why is it your go-to simulation tool?
I might be biased because, of course, the first one I was ever exposed to was Ansys,
Okay.
but I have been exposed to others afterwards. So when I joined Linear Transfer, and that's a company out of Barrie, it was a position I held just before coming to SCIEX. They were using finite elements, but they were using whatever is available in Inventor. At first, it was the very basic, which had nearly no functionality, in my opinion. You could not check the metrics of your mesh, so you had no idea if your mesh was good or bad. I mean, you had to eyeball everything. And this is where I learned where they were saying, oh yeah, we use it, but we use it as an eyeball tool because the deflection results are out to lunch. They don't mean anything. We just use it as a gauge. And I thought to myself, what are you talking about? And when I went to look into that program more, it just didn't have the same strength. And then they upgraded to NASTran. NASTran was better, but I still felt too limited. So really what I found thus far using Ansys is all of its ability to integrate between all the different multiple physics. And I think a part of what makes junior engineers or engineers just getting into Ansys a little bit apprehensive due to the complexity, well, that's exactly what I love. It's that complexity, that additional power. There's so much you can do with Ansys. And there's a lot of customizability to even cater Ansys to your specific industry or problem. So not being limited and having the ability to do really out of the box stuff that's not in the default installation, that's what really attracts me to Ansys in particular. You have a lot of power, a lot of complexity, but a lot of power, which means a lot of room for all sorts of things that you can manage to do in the software.
So, if you're able to talk about any of them, are there any new exciting developments coming up with SCIEX that you're able to share with us? I know, some of this stuff is proprietary information, so you can't really share too much, but, I didn't know if you had anything coming up or anything that you guys are working on, any new technologies that maybe you guys can share that we should keep a lookout for?
Well, I know as it goes for mass spec, so mass spectrometry, our latest device that has been released is the 7500. And it is apparently, and I was just getting into this because mass spectrometry was completely new to me when I joined SCIEX, but the 7500, I believe in its class, is the most accurate in the market. What the comparison made in layman terms that the chief engineer of the company made was that basically, if you were to put 1 grain of sugar in 3 Olympic-sized pools, our machine would be able to detect that 1 grain of sugar. It's that sensitive to be able to pick out components in a chemical sample.
That's awesome. Well, it really has been wonderful kind of getting to know you and your experience with Ansys. I mean, you're obviously a very brilliant individual, and you're going to be a great mentor for so many young aspiring engineers. And I'm excited to just share your profile with them as well. And hopefully if they reach out to you, you can reply and just kind of coach them or send them a good, encouraging message. But we have, we really appreciate your business and we really enjoy talking to you. And I want to have SimuTech send you like an Ansys superhero cape. Like I'm going to tell Scotty this after, and that's something that we should send to you. And you could show your kids that too, because you're our little engineering superhero.
Thank you. I appreciate that.
So I wanted to thank you so much for, joining us today. And it was very nice to meet you.
Well, it was my pleasure.